While putting together this show, I often find myself thinking, wow, this release is like that science fiction plot line, or, oh, this is new. I hope someone uses this in a story. Most of the time, when I think things like that, I'm reading about black holes or star formation or planets of new and weirder layouts. Sometimes, however, I read stories and think, yeah, that has to do with tech, and maybe we don't want to go that direction. I can't tell you if advances in AI are going to lead us to Cylons or if climate change is going to destroy our civilization like it destroyed the civilization in that one episode of Star Trek, The Next Generation. What I can tell you is science fiction is how humanity explores the consequences of our behavior. And these fictions can sometimes give us insights into possible futures we probably want to avoid. And this includes the future shown in Wall-E, or at least some of the future shown in Wall-E. When our little robot friends depart the Earth, we see that it is surrounded by an almost impenetrable shell of satellites and satellite pieces. When the movie came out in 2008, this seemed like a far-off possibility. But according to satellite cataloger Jonathan McDowell, there are now 18 planned satellite constellations like Starlink. These constellations will contain 543,811 satellites. This is a whole lot of missions to try and keep from colliding. And all it takes is one particularly bad collision to transform the more than 500,000 objects from useful technologies to a shield of shrapnel that protects our universe from us by trapping us here. In our closer look today, we are going to look at early warning systems that are being developed and how future, more highly mobile satellites can both do good and create chaos. I don't think we have a Wild West anymore, but we do have a Wild Up. Can we make that a phrase? I think we should make that a phrase. The Wild Up. All this and more is coming to you right here on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Everything is a cycle. We don't always know all the parts of the cycle, but our universe truly is wheels within wheels within wheels. One of the cycles we've studied the most is the cycle of star formation. With each generation of stars, we've seen our universe get more complex and more full of possibilities. Stars in all their diversity require different mixes of atoms, and planets require the heavy atoms generated across generations of stars. While we know that modern stars and the most ancient stars were different, most of our understanding comes from running computer models, which often fail to predict some of the weird and wonderful things our universe throws at us. Luckily, telescopes can act as time machines thanks to the finite speed of light. As I look at my camera, I see how it appeared the smallest fraction of a second ago. When I look safely using eclipse glasses at the sun, I am seeing it as it appeared 8 minutes ago. The further and further away we look, the longer it takes light to travel to us, and thus the older the light is when it reaches us. When we look at light that has traveled 5 billion light years from a galaxy, we see the galaxy as it appeared 5 billion years ago. Our best modern time machines are the JWST and ALMA, with its 6.5-meter mirror and location in space. JWST is able to see faint objects whose light came from the early universe. On Earth, ALMA does similar work in even redder colors of light. Together, they can capture everything from hot young stars to cooling gas nebulae. Case in point. In a new paper in the Astrophysical Journal, researchers led by Yoichi Tamara used ALMA to study star formation when the universe was just 600 million years old. And they were able to resolve features as small as 1,000 light years across. That object? It's cataloged as MAX 0416Y1. By looking at the system and the colors of light emitted by dust and by ionized oxygen, the research team could see where hot star formation had started, where cool dust waited to form stars, and where neither dust nor young stars were hanging out. They found a hollow region, seemingly carved out by the explosions of young stars, completely surrounded by an intermixed nebula of dust and forming stars. Over time, the observations indicate the stars will form into massive clusters. The details of how that will happen? Well, that may be research for the JWST to take on. As team researcher Takuya Hashimoto explains, these were extremely difficult observations. Quote, "It corresponds to capturing the extremely weak light emitted by two fireflies located 3 centimeters apart on the summit of Mount Fuji as seen from Tokyo, and being able to distinguish between those two fireflies. In the future, more detailed information can be obtained by conducting high-resolution observations of these star clusters themselves, using instruments such as the JWST and the planned extremely large telescopes." End quote. One of our greatest frustrations in astronomy is that we want to do more science than we have telescopes to do. Projects like looking at MAX 0416Y1 have to wait their turn as everyone proposes for their best projects to be observed. In a new set of images and spectra, researchers did get to use the JWST to explore a region of the sky known to contain a distant quasar. These active galaxies contain a feeding black hole and emit so much light from the dense region around the black hole that sometimes only the core's star-like glow is visible. The light from this particular quasar headed our way when the universe was just 830 million years old. It was originally observed by both ALMA and the much smaller Hubble Space Telescope. With these observatories, the quasar cataloged as J0305-3150 appeared to shine alone from the early universe. With JWST, astronomers were able to see that J0305-3150 is hanging out, all lined up with friends. Literally, these systems are all lined up, forming a 3 million light-year long filament. These results are posted in a pair of papers in the Astrophysical Journal Letters, led by Zhenyi Yang and Fiji Wang. It's totally normal to find galaxies grouped together. What is remarkable here is how early in the universe we're seeing such a well-defined thread of systems. As the story goes, our universe formed with a slightly lumpy density. Where there was a little more material, gravity gathered in mass, and over time gathered in enough gas to form galaxies and their stars. According to Wang, quote, "This is one of the earliest filamentary structures that people have ever found associated with a distant quasar." End quote. And this is the first time a structure of this kind has been observed at such an early time in the universe and in 3D detail. Quasar J0305-3150 is just the first of 25 systems that will be observed as part of the Aspire survey. All 25 systems are shining from the early universe, and this survey should allow us to answer questions around how much structure formed and how star formation took place in the first billion years when our universe became transparent to starlight. As we get more results about additional systems, we'll bring them to you right here on EVSN. Before we go to break, I want to highlight one more piece of news. In a new paper in the journal Nature Astronomy, researchers Garrett Lewis and Brendan Brewer show evidence for time appearing to tick slower in the early universe. According to Relativity, as our universe expands, we should see the most distant events playing out in slow motion. The details on how this works are super cool and super complex. For now, all you need to understand is Einstein's work predicted we should see the distant universe doing things in slow motion. And looking at 190 quasars at a variety of distances, Lewis and Brewer were able to see this prediction play out. Essentially, as quasars eat material, they can flicker and flare. As they describe it, by, quote, combining the observations taken at different colors or wavelengths, green light, red light, and into the infrared, they were able to standardize the ticking of each quasar, end quote. Statistical analysis of all these ticking systems showed that we perceive the quasars to tick slower and slower the farther out we look. This is sadly an us thing. Time didn't actually tick slower to any observers in the early universe. It just seems, thanks to relativity, that time slows with distance in an expanding universe. Does your brain hurt yet? I kind of like it. After the break, we're going to bring things back down to Earth, or at least down to other Earths. Up next is exoplanets. Stay tuned. A fair amount of astronomy consists of theorists coming up with mathematically valid ideas of what is possible, and then everyone debating if the universe would actually do something that wild. This is a common issue in particle physics, where researchers have predicted all manner of particles through theories such as supersymmetry. In that particular case, the universe seems to have responded with a solid, nah, not going to do that. Other theories, however, do eventually get proven true. And a lot of naysayers are left going, huh? As the universe has once again shown us that if you create enough things, pretty much anything can happen. One of the theories a lot of us were willing to discount was published by Gregory Laughlin and John Chamber in 2002. In their paper, they suggested that if two planets had just the right separation and were just about the same mass, they should be able to share an orbit. This particular separation takes advantage of the gravitational balancing points that exist wherever a small object orbits a large object. These points are called the Lagrange points, and we have them in the Earth-Sun system, and we use them as holding zones for satellites like the JWST and the Solar Dynamic Orbiter. And with the Jupiter-Sun combination, we find Trojan asteroids hanging out in the leading and trailing L4 and L5 Lagrange points. In Laughlin and Chambers' paper, they proposed that two worlds could orbit in one another's Lagrange points if they were essentially the same mass. The leading planet would sit in the leading L4 Lagrange point of the trailing planet, and that trailing planet would sit in the trailing L5 Lagrange point of the leading planet. The math all works out, but the probability of two similarly sized planets landing in just this position combination just seemed impossible. So we haven't exactly been going out of our way to find a solar system with this particular geometry. But one solar system decided to show us what just might be this unexpected two-planet kind of a system. Cataloged as PDS-70, this system was observed by ALMA and found to have a planet-forming disk, at least two planets, and what appears to be a blob of a past or future planet in the inner planet's Lagrange point. This work is published in Astronomy and Astrophysics and led by Olga Basharbi-Ruza. It is currently unclear if the fuzzy blob is a lasting feature or just a temporary blob of dust. It also isn't known if this is a chance alignment or if these two objects are truly orbiting together. To answer these questions, the team is already planning to revisit PDS 70 in 2026 to see if the orbits have continued alongside. If this is a two-planet system, this is a sci-fi future made reality. This is that system with two worlds with the same length year and the same habitability, orbiting together and evolving together out among the stars. We are only able to predict systems like this and understand our universe beyond our Earth for one simple reason. The rules of science are universal, and that means they are constant throughout the universe. And this is just as true across distance as it is across time, as it is across size. Consider the Grand Design Spiral Galaxy. Researchers are still working out the details of how these beautiful systems come to be. But we do know that wherever these perfect spirals exist, a companion galaxy exists as well. This has led to a basic understanding that these spiral structures require the combined gravity of the main galaxy and the companion galaxy. If grand design spiral galaxies require a second smaller mass, reason tells us that other disks of material should also be able to have spirals when there is a proportionally sized companion. Researchers had even speculated that the dust disks around young stars should sometimes form spirals when influenced by planets. Again, all the math worked out, but seeing spiral patterns in dust is hard, and up until now, no examples had been seen with a planet. But thanks to the Large Binocular Telescope and its twin 8.4-meter mirrors, we now know that a giant planet, cataloged as MWC 758c, is twisting the dust around its young star into exactly the spiral that was predicted. This work is published in Nature Astronomy and led by Kevin Wagner. This system is just a few million years old, and everything is still in flux. This dusty disk is only a temporary structure, and in time, most of the dust will form planets, and what is left will be blown out of the system or fall into the star. According to Wagner, quote, "I think of this system as an analogy for how our own solar system would have appeared less than 1% into its lifetime. Jupiter, being a giant planet, also likely interacted with and gravitationally sculpted our own disk billions of years ago, which eventually led to the formation of Earth." End quote. Systems like this should be fairly common in star-forming regions. And for a long time, folks have wondered why we haven't seen them. With this particular set of observations, researchers looked at light produced by cooler systems. It turns out large young planets don't appear as hot as we'd expected. According to team researcher Stephen Ertel, quote, "Either this is a planet with a colder temperature than expected, or it is a planet that's still hot from its formation and it happens to be enshrouded by dust." End quote. Whatever the specific case, this kind of a world is right in the sweet spot for JWST. And researchers are already hoping that future observations of young solar systems by this young telescope will be able to find more spiral disks and tell us exactly what is going on. Because we live on a planet, it is easy for us to think of stars and planets as separate things that are held together by gravity and don't have all that mutable an effect on one another. It's easy to think that, but it's also wrong. As They Might Be Giants told us, the sun is a mass of incandescent gas, and that gas and all the magnetic fields and high-energy particles associated with it can rain chaos on our planet's atmosphere. or plunge us into a mini ice age by being utterly boring for a while. In general, our sun has an 11-year cycle during which it goes from quiet to spotty and chaotic to quiet again. As humans, we've so far recorded over 24 solar cycles, as well as a weird prolonged quiet phase from 1650 to 1715. The past several cycles have been smaller cycles with less activity, but this cycle, number 25, is so far on track to exceed expectations. And it has already triggered blackouts in radio communications and major aurora into the continental United States. If you have always dreamed of going on a vacation to see aurora, which I have, now is your time to plan. From now until 2029, we should be experiencing regular solar activity. The Parker Solar Probe made its first close-ish pass to the sun in 2018 and is now making several close passes a year. It just completed its 16th pass on June 7 and has returned its data for analysis. Currently, Parker is scheduled out through December 2026, when it is slated to make one of the closest approaches. This time span means Parker will have the chance to monitor the sun throughout half its cycle and show us up close just what is driving the sun's activity. If you want to keep track of the sun's day-to-day influence on Earth and an effect called space weather, I recommend checking out the site spaceweather.gov. After a break, we're going to take a look at the massive missions milling about the Earth and just what this solar max might mean. Stay tuned. According to NASA, more than 37,000 pieces of debris larger than a softball currently circle our planet alongside the nearly 12,000 individual satellites. Each of these objects has its own specific path around the Earth, but a lot of these paths intersect, and as researchers and satellite operators look to the future, it's becoming progressively more complicated to figure out how to prevent satellite collisions while also maintaining the longevity of each spacecraft. The age of satellites began on October 4th, 1957, with the launch of Sputnik by the Soviet Union. Launched into a highly elliptical orbit, Sputnik spent roughly 3 months going from a maximum height of 939 kilometers and then plunging down to an altitude of 215 kilometers or less. The mission didn't carry any of the modern engines or fuel needed to maintain its orbit. And with every close approach to the planet, the top of Earth's atmosphere dragged on Sputnik just enough to lower it until it burnt up in the atmosphere on January 4th, 1958. The Earth's orbit isn't an entirely stable place for a spacecraft. Below about 900 kilometers, the Earth's atmosphere will slowly drag on missions and eventually pull them out of orbit. The lower the spacecraft and the more active the atmosphere, the faster that decay. Above about 900 kilometers, radiation from the sun is going to dominate and play its own role in slowly changing orbits. Basically, if you put something in orbit around the Earth and ignore it, that thing is going to wander away and keep wandering away as its orbit evolves at the whim of our atmosphere and our sun. And we're about to experience the first solar max since companies like SpaceX started launching constellations of small satellites into space. And no one is exactly sure what is going to happen in this new era of mega constellations. When the sun releases a flare or other burst of energy, the Earth's atmosphere will respond by expanding outwards. This can be deadly to satellites in very low Earth orbits. In fact, in January 2022, a solar storm hit Earth right after the launch of a set of 49 Starlinks. These tiny satellites start out on an orbit just 210 kilometers above Earth and then use onboard thrusters to climb into their final orbits around 550 kilometers up. When the flare hit, the expanding atmosphere created so much drag on the spacecraft that 38 of them were destroyed and burned up in the atmosphere. Right now, we only have hours of warning when a flare has been released in our direction. And this means we can't just launch missions when we know low Earth orbit is safe. Every launch is a risk. And as we approach solar max, the risk is only going to increase. Put another way, we are launching small satellites, some as small as soda bottles, into Earth orbit, knowing the sun and our atmosphere can just push them around. And not all of these spacecraft can maneuver. Many small satellites don't have thrusters, and many spacecraft still orbiting have long since run out of fuel or simply died an electronic death. When the sun expands out our atmosphere, all these uncontrolled missions are going to have their orbits changed in ways that relate to their mass and their shape. Same story for all the debris. And it gets worse. Because our atmosphere is a bit unpredictable, we can't know exactly how these orbiting objects are going to move. If you happen to control an expensive maneuverable spacecraft in low Earth orbit, you're probably going to be paying someone to not just watch your mission and update you on where it ended up, but you're also going to be paying for data on where everything near you moved so you can make sure you don't end up in a collision. The U.S. Space Force takes the lead in general mission tracking here in the U.S., and there are a variety of services out there that are using both optical telescopes and radar dishes to keep track of orbiting objects. The company with the largest name recognition is probably Leo Labs, a company that actively uses its social media to draw attention to close encounters in orbit. From tracking the May 16, 2023 close approach of a newly launched Chinese satellite and dead Soviet mission, to tracking the 2020 close approach of the decommissioned IRAS satellite and a dead U.S. science mission from 1967. They are showing over and over why we have to keep an eye on the skies to both steer what can be steered and dodge fast from any debris created by collisions. And this is where spacecraft longevity and a game of chicken can take place. Every month, missions from many companies and space agencies are forced to move out of the way to avoid a collision. Spacecraft can only carry so much fuel, and we don't have a readily available way to refuel or move missions at this time. I have confirmed from multiple sources that sometimes satellite operators can end up on the phone with one another, bickering over who has to use fuel to move and avoid a potential collision. This is best described as chaotic and inefficient, but this is modern space flight at its finest. There are no on-orbit police, and once something is launched, no one can really stop you from doing anything. It's a thing. So what do we do? If you're me, you worry about the Kessler syndrome, a theoretical situation in which one bad satellite collision can lead to a runaway series of collisions, like cars colliding in a winter storm. And just like car crashes can close down a highway, satellite collisions have the potential to close down orbital space, which is something to avoid. So what should we do? Leo Labs is taking one path by very carefully monitoring satellite positions and helping folks, including paying customers, avoid collisions. Lieutenant General John Shaw, the Deputy Commander of the U.S. Space Command, is taking a different tactic. At an event at the Mitchell Institute for Aerospace Studies, he commented that, quote, "The way we've been doing space operations since the dawn of the space age, we've been doing it wrong. We launch a platform into orbit, and we tend to leave it right in that orbit. That's not going to be sufficient anymore. We can't have those constraints in the future. And so we're trying to articulate a requirement to the Space Force that we need to be able to have a sustained space maneuver for those platforms." End quote. The idea of having a mobile space platform is twofold. On one side, if our missions are designed to be constantly on the move, we won't need as many spacecraft to be able to study developing situations. Just like a news helicopter can maneuver to catch everything going down in its viewing area, A mobile space platform will be able to maneuver to catch what's going on above or below a swath of different orbits. These kinds of built to move systems can effectively reduce how many spacecraft we need on orbit for some tasks, while also actively working to stay out of harm's way. These platforms also have more nefarious uses, like snuggling up next to other nations or corporate competitor spacecraft to monitor their transmissions, but that's a different story. To make this kind of a mobile space fleet a reality, we have to also make refueling in space or cheaply building spacecraft a reality. But this is a technical challenge that is already being addressed. Northrop Grumman has successfully tested a satellite designed to grab and move existing spacecraft, essentially turning them into mobile platforms. And numerous companies are exploring how on orbit refueling can work. Plans for the lunar version of Starship, which will ferry people from the lunar surface to space, require orbital refueling. This is our future, provided we avoid collisions. Here's to hoping technological advances make this possible before bad luck triggers a Kessler syndrome. The race is on, even if not enough people are talking about it. Up next, we're going to look at robots for the moon and recent launches, landings, and other news from the launch pad. Stay tuned. Assuming we're able to maintain our access to space, our most effective way to explore other worlds will be with robots. They don't require silly little things like air or sleep or healthcare and retirement benefits. They can be crammed into small containers for transit, and they'll just unfold and roll on like that was the best thing that ever happened. If one dies, the entire community will mourn. But there is unlikely to be a congressional investigation like if an astronaut dies. Robots. Robots without too much AI are our science doing friends. I'm not ready for Cylons. Please don't make Cylons. And I don't mean Boston Dynamics when I say robots. There's a lot of other games in town. The European Space Agency is currently testing a small pack of multi-legged explorers that can swarm over scientifically interesting sites. As team member Philip Arm explains, quote, using multiple robots has two advantages. The individual robots can take on specialized tasks and perform them simultaneously. Moreover, thanks to its redundancy, a robot team is able to compensate for a teammate's failure. End quote. Currently, these robots are being tested in rocky terrains that mimic the kinds of obstacles they might encounter on the moon. It's unclear when they will get bundled into a spacecraft and sent on a 250,000-mile journey, but when it happens, I hope to be here to cover it. And speaking of spacecraft, next up, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launch Pad. Hey, Eric.
Hi, Pamela. There was a nice variety of launches this week from the US, China, New Zealand, and India. First up was a Long March 2C with test internet satellites from the Qiuquan Satellite Launch Center on July 9th. Two satellites for a planned internet constellation were sent up on the three-stage rocket. This new constellation is not like Starlink. It uses a smaller number of satellites in a larger orbit. Next up is the second flight of the Zhuge 2 rocket on July 11th, also from Qiuquan. It's a big spaceport. The Zhuge 2 is a large rocket developed by a Chinese company named Landspace. It is designed to put 6 metric tons into low Earth orbit. Unlike most of the other private rocket companies in China, Landspace uses liquid methane and oxygen-fueled rocket engines on the Zhuge 2. This flight carried a dummy payload, basically a large chunk of metal, to orbit, a common practice on launches of new rockets. The launch was successful, making Landspace the first company in the world to successfully launch a methane-powered rocket into orbit. On July 14th, the Indian Space Research Organization launched their Chandrayaan-3 mission. This is a follow-up to the mission that crashed on the moon in 2019. ISRO used their largest rocket, the LVM-3, to launch the lander and its propulsion module. Unlike the previous mission, the orbiter was significantly scaled back, It still has a solar panel, but only one instrument. The orbiter launched on Chandrayaan 2 is still functional, so there is no need to launch another one. The lander had several major improvements to its system. The five main engines were replaced with four smaller ones because the lander is heavier. In the event of a failure, the lander can still land on two of the four engines. The lander's legs were lengthened and wider feet were added. It can now survive an impact 1 meter per second faster than it could with the thinner legs. The fuel tank in the first design was replaced with a larger one, as was the main solar panel. The new lander also features a laser ranging system to add redundancy with its existing measurement instruments. The last major change was to the flight software. The first landing failed because it landed short of the intended location and overcorrected trying to get to the intended spot. Chandrayaan 3 will allow itself a larger area to land in to compensate. It is also more tolerant of sensor failures and thrust disruption. Chandrayaan 3 will take about a month to get to the moon after a series of engine burns from its propulsion module. Landing is expected in late August. Also this week is a Rocket Lab launch from the main spaceport in New Zealand on July 17th. The primary payloads were four satellites from NASA's Starlink mission. They will demonstrate autonomous positioning, networking, and decision making as a set of closely orbiting satellites. Also on the rocket were two weather monitoring satellites from Spire Global and one from Spaceflight Laboratory of Canada. It will be operated by Telesat, a Canadian communication satellite operator, continuing testing of their planned low Earth orbit communications constellation. In addition to the launches we've talked about, there are also four launches of Starlink satellites from all three of SpaceX's active pads in Florida and California. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 52 launches, China's had 27 launches, India and Kazakhstan each have had 5 launches, New Zealand and Russia have had 4 launches, French Guiana and Japan each have had 2, and Israel, North Korea, South Korea, and the United Kingdom each have had 1. Of those 105 launches, there have been 5 failures, reminding us that space is hard.
Thanks, Eric. We normally end these episodes with a heartwarming fact or something from history. This week, there were so many different amazing things to pick from that I couldn't pick just one. But I was able to narrow it down to two. In July 1969, 54 years ago, Neil Armstrong and Buzz Aldrin landed on the moon while Michael Collins orbited above. While all three lived long lives, only Buzz Aldrin, at age 93, is still alive. I, for one, hope he will still be around when humans are able to one day return to the moon. That summertime flight to the moon started a 3.5-year epic of human exploration of the moon. It has always amazed me that Apollo missions were only planned through 1972. Even the original journey of the Starship Enterprise was expected to last more years. This is your reminder that Apollo wasn't so much a long-term science program as a project designed to show we can and will overcome any problem. We will climb the highest mountain, and we will walk on the nearest world. And then we will go home and look back on our pictures for at least 54 years. Time just keeps ticking, and we can't always do all the things we want to do. But while the return to the moon seems to be forever slipping into the future, we have made other amazing accomplishments. Somehow, on Christmas Day 2021, JWST finally made its way into space. On July 11th, 2022, President Joe Biden released JWST's first image. Now, a year into taking science data, the Space Telescope Science Institute is releasing a spectacular image of Rho Ophiuchi Nebula. I love this image because it shows space as many colors and textures. And if, like me, your brain likes to find non-existent patterns, this image demonstrates there are very silly penguin images naturally occurring in space. And that's it for now. Good night, everyone, and remember to go out and look up.